Hello.
Okay, so let me please introduce you. Our next speaker is Beni Yoshida, who's going to tell us about fault-tolerant logical gates in quantum error correcting codes. Thank you.
So it is my great pleasure to be here. So today I'm going to talk about fault-tolerant logical gates in quantum error correcting codes. So this is a joint project with Fernando and Pastawski, who is in the audience, I think. And the paper is available online on this following archive number, and I forgot the journal reference number, but you can look at archive paper, which is what usually people do. Okay, anyway, so what is the motivation? So underlying difficulty in quantum information science is the fact that quantum entanglement decays easily. Therefore, we need to protect a qubit by using quantum error correcting code. So here is an example. You prepare an input state and run encoding circuits so that you encode information so that local and small amount of errors do not destroy the encoded information. And ideally, we would like to perform quantum computation in some protected code word space of some good quantum error correcting code. And ideally, we want to perform logical gates by transversal unitary gates. That is a unitary operator which has tensor product structure, each unitary acting on each qubit. Then, if such a transversal implementation is possible, then local errors do not propagate to other qubit. So that's very good. But if transversal implementation is not possible, then local errors may propagate to other qubits, which is very bad. Okay, but unfortunately, there is a no-go theorem due to Easting and Knill, which says that, well, transversally implementable logical gates are not universal for quantum computation. Then is this the end of quantum information science? But of course not, because there are many clever methods to avoid the theorem. But the point is that if you restrict your attention to transversal logical gates, there is not much you can do about it. And I personally feel that this is one of the most important results in quantum information science. So recently, Bravy and Koenig further generalized this result, and they actually consider more physically realistic setting. So imagine that you have a lattice of qubits or spins. So spins are sitting on lattice side, and they are interacting locally with each other. And as a fault-tolerantly implementable logical gate, they consider not only transversal logical gates, but also logical gates which can be implemented by local unitary transformation, because such a local unitary transformation will not make errors propagate that much. Under this problem setting, they prove the following theorem, that is for a stabilized Hamiltonian in d spatial dimensions, fault-tolerantly implementable logical gates are restricted to the dth level of the Clifford hierarchy. So what is Clifford hierarchy? Well, it is just a hierarchy of sets of unitary gates acting on n qubits. At the lowest level, you have the Pauli operator group or Pauli operator set, x, y, z, and their tensor product. Second level is the so-called Clifford gate, which brings Pauli operator to Pauli operator. So, and the third level, P3, brings Pauli operator to P2 operator. So in general, PM gate brings Pauli operator to PM-1. So by using these relations, you can recursively construct the Clifford hierarchy. And in general, roughly speaking, logical gates from the higher level of the Clifford hierarchy is much more difficult to implement. For instance, in this theorem, it says that in this spatial dimension, all you can do is restricted to this level of the Clifford hierarchy, PD. Okay, so here is the plan of today's talk. So in today's talk, I would like to explain and present some applications and generalization of the Bravy Koenig theorem. In particular, I will talk about generalization to subsystem quantum error correcting code, and I will talk about a new upper bound on the erasure threshold, some no-go theorem on self-correcting quantum memory, and some new upper bound on code distance. Okay, so let me briefly review how we can prove Bravy Koenig theorem. So the key idea is the so-called logical operator cleaning, so which says the following. A logical operator can be cleaned from a correctable region. A correctable region means that a region which supports no logical operator at all. So let's look at an example. So in this example, I have a partition into region A and B. Now assume that A is correctable. Now I consider logical operator U, which is supported jointly over A and B. Then since A is correctable, I can always find the equivalent logical operator U prime, which acts in the same way on the code word space, but it is strictly supported only on B. So in this sense, I can clean logical operator from region A. So that's why we call it cleaning. And this cleaning allows us to prove the following lemma. So imagine that we have a code and you split the entire system into n plus 1 regions. And let's assume that these regions are all correctable. Then it turns out transversally implementable logical gates are restricted to mth level of the Clifford hierarchy. So for example, in this case, I split the system into 4 regions, and if these 4 regions are all correctable regions, then it turns out all you can do is restricted to P3 gate. Then how do we prove such a lemma? Well, let us first consider arbitrary Pauli logical operator, V0, V1, and so on. But here we assume that these RJ regions are correctable, which means that I can choose V0 so that I have no support on R0. Similarly, V1 has no support on R1, and so on. Now let us consider a transversal logical operator U0, which is supported all over the lattice. And I would like to prove that this belongs to PM. So this is the goal. For this purpose, I need to consider a group commutator between U0 and V0. But the point is, V0 has no support on R0. This means that U1 has no support on R0. Okay, then next, I will consider the group commutator between U1 and V1. Then since U1 has no support on R0 and V1 has no support on R1, it turns out U2 has no support on R0 or R2, R0 or R1. And by keep doing this, at the end of the day, you can prove that UM has support only on RM. But we assumed that RM is correctable region, which means that, well, UM is just a complex phase on the, it's proportional to the identity on the code word space. From that information, you can deduce that UM-1 belongs to P1. And then actually you can prove that U2 belongs to PM-2, U1 belongs to PM-1, and so on. Then you can prove that lemma. Okay, so with this lemma in hand, we can easily recover the Bravy Koenig theorem. The key idea is we can split the d-dimensional system into d plus 1 correctable regions. So here's an example for 2D. I split it into R0, R1, R2. And since it's a not partition into 3 regions, so all I can do is restrict it to P2. And here I implicitly use the so-called union lemma, which says that the union of spatially disjoint correctable regions is also correctable. But unfortunately, this is only true for stabilizer code. It turns out this is not respected in subsystem code, and this causes us a lot of problem in later generalizing this result to subsystem code. Okay, so having proved the Bravy Koenig theorem, now I would like to talk about upper bound on erasure threshold. So imagine that you are an experimentalist. I know you are not, but you are an experimentalist. Then you want to physically realize the code in your lab. But in reality, there may be some qubit loss or some qubits may be damaged. So I want my code to be fault-tolerant in the sense that even if some fraction of qubits are lost, I want to recover the encoded information. So for that purpose, I want my code to have finite erasure threshold. And of course, this is a very important problem from theoretical viewpoint, because if you think about error threshold for depolarizing channel, it is always smaller than erasure threshold. So in order for the code to be useful or fault-tolerant, we definitely need to have a finite loss error threshold, erasure threshold. Okay, so here is our result. Suppose that you have a code whose loss tolerance is strictly larger than 1 over n, where n is some positive integer. Then it turns out transversally implementable logical gates must belong to Pn-1. Reversing the argument, if the code has non-trivial Pn logical gate, then its loss tolerance is upper bounded by 1 over n. Okay, so here's the result. And the proof is actually extremely simple. It's 4 line. So we assign each qubit to n regions uniformly at random, like R1, R2 to Rn. Then all these regions must be correctable since we assume that error threshold is larger than 1 over n. So we partition the system into n correctable region, which means that all we can do is restricted to Pn minus 1. That's it. So even though the proof is very simple, it has interesting implications. So first, as you know, the Toric code has 1 over 2 loss error threshold, which is related to the theory of percolation. And as you know, it has a transversally implementable P2 logical gate. So the Toric code actually saturates our bound. Next, if you try to construct a code with growing n, then such a code will never be fault-tolerant because loss error threshold will go to 0. Finally, the topological color code in this partial dimension has PD logical gate, which means that the color code's loss threshold must be equals to or less than 1 over d. So one additional remark is we explained this result to Leonid Priadok, and then he said like by combining our result with his result, we can prove some interesting theorem. So this is the result. So we consider a stabilizer code with at most k-body generators. Then if the code has transversely implementable PD logical gate, then it turns out k must grow linearly with respect to d. And I like this theorem because currently the best, well, probably well-known code is a d-dimensional color code, which has 2 to the d-body interaction, so it's exponentially growing. So this theorem leads to a question of like whether we can do this with fewer body interaction terms or not. Okay, so second result concerns self-correcting quantum memory. So self-correcting quantum memory is an idealistic quantum memory device that would correct errors by itself without doing any active error correction because of the large energy barrier separating 0 state, 1 state, and their superpositions. And this is closely related problem of topological order at finite temperature. So now here's our result. So if a stabilizer Hamiltonian in 3 spatial dimensions has fault-tolerantly implementable non-Clifford logical gate, then the energy barrier must remain constant. Okay, so here's a proof sketch. First, I consider partition into 3 regions, R0, R1, R2. And these regions are like a tube-like object. Now, suppose that there's no string-like logical operator at all in this system. Then R0, R1, R2 are, of course, correctable region, which implies that the code can have at most P2 gate, which is Clifford gate, leading to a contradiction. So the code must have a string-like logical operator, implying that the energy barrier is constant. So this is quite surprising because I think implementability of logical gate is a property of a code word space, but the energy barrier is a property of a spectrum or Hamiltonian, but they are somehow related each other. And here are some comments. Has 3D cubic code or Michnik is 3D welded code. Both of them have diverging energy barrier, which implies that they cannot have non-Clifford gate. And on Friday, we will hear interesting proposal by Brel on self-correcting quantum memory. But the point is, it is a proposal for self-correcting quantum memory, which means that it cannot have a non-Clifford logical gate. And finally, currently the only known example of code with non-Clifford logical gate with diverging energy barrier is constructed in 6 dimensions by Bombin. But this theorem says that maybe we can do it in 4D. So that's an interesting question, I think. So third result I would like to introduce is talk about is code distance. So as you know, code distance is a quantitative measure of the reliability of encoding. So we would like to have a code with large code distance. So here's our new result. So if a topological stabilizer code, I mean stabilizer code with local generators in this partial dimension has mth level logical gate, then its code distance is upper bounded by L to the d plus 1 minus m. Now let us compare this result with the known result by Bravy and Threshold. So they prove that for local stabilizer code, the distance is upper bounded by L to the d minus 1. So for a code with non-Clifford gate, our bound is actually tighter. And it turns out d-dimensional color code has distance equals to L. And it has PD gate, so it turns out the color code saturates R bound. And I will skip the proof of this theorem because actually the proof is very similar to the technique we used to prove this no-go theorem on self-correcting quantum memory. So finally, I would like to talk about generalization to subsystem code. So as you know, subsystem code is a generalization of the stabilizer code. In stabilizer code, we start from abelian subgroup of Pauli operators. But in the case of the subsystem code, we start from non-abelian subgroup of Pauli operators. And I'm not going to talk about the details of how subsystem code works, but the point is it is often the case that in subsystem codes, you can generalize the code with fewer body interaction compared to stabilizer code. So this may give you a hope that by using subsystem code, maybe we can break the I don't know, the Bravy Koenig bound. But it is not the case actually. So here is the main result. So for this partial dimension, subsystem code with local generators, fault-tolerantly implementable logical gates are restricted to PD if the code is fault-tolerant. Okay, so then what is the difficulty in generalizing this result to subsystem code? Well, it is due to the breakdown of the union lemma. As you may know, the subsystem code has two types of logical operators, which are called dressed logical operators and bare logical operators. But the point is, even though the gauge generators are locally constructed, stabilizer operators may be non-local. So if you think about dressed logical operator, jointly supported on A and B, but there may be some stabilizer which is very non-local and overlapping with region A and B, which means that I cannot decompose this dressed logical operator into smaller parts, and this causes a trouble to us. Then let us briefly recall how we proved the Bravy Koenig theorem. That is, I use the property that union of these tiny dots is also correctable, but this part breaks down. So in order to avoid this problem, we actually took an alternative approach. So we assume that the code must have a finite loss error threshold in order for the code to be useful, of course. So the point is, suppose I lose some fraction of qubits from my code. Then with some finite probability, I can always find a big region. It's finite, but it's very big cluster of region where all the qubits are lost. And such a region or cluster always appear with some finite probability. And such a cluster is shown with red dots. And now the point is, of course, the union of these red dots is correctable. Otherwise, the code does not have a loss error threshold. So we use this red dot region as R0. Then by carefully connecting R0 dots, we can construct a cubic grid and we can split the system into D+1 regions. Then it turns out we can recover the Bravy Koenig theorem. So as a result, we can prove that fault-tolerantly implementable logical gates are restricted to PD. And so one remark is, in order to recover this result, we needed to assume that the code distance is growing, at least logarithmically, in the system size. Okay, so here's a summary of the talk. So we have Bravy Koenig theorem, and I explained the application and generalization, like generalization to subsystem codes and erasure threshold, self-correcting quantum memory, and code distances, and so on. And well, these days there have been lots of interesting discussion and debates going on concerning properties of fault-tolerantly implementable logical gates. And I'm still interested in this problem, and I think Fernando Pastawski, who is a co-author, he is also interested in this problem. So we are still working on this kind of project. So in the remaining time of my talk, I would like to briefly talk about our new paper on closely related subject. So this is again a joint work with Fernando Pastawski, but this time Alexander Kubica joined us, and he did an awesome job. So the basic question which drove us is the following: what is the difference between the Toric code and color code? As you have seen in my talk, the color code often saturate important bounds concerning fault-tolerant implementability of logical gates. And there will be a talk by Bombing on some additional new interesting feature of the color code. But then our question is, what makes the color code so special, distinct from the Toric code? So the new paper has 3 main results. First result says the following. Well, if you think about the color code on a closed manifold, actually color code and the Toric code are actually the same. Our new theorem says that in D spatial dimension, color code on D dimensions on a closed manifold is actually equivalent to multiple decoupled copies of the D dimensional Toric code up to local unitary transformation. So this extends the known result in 2D, but also we give an explicit recipe to disentangle color code to Toric code. Then is color code and the Toric code completely the same? Well, it's not really the same, because some subtle difference appear when we think about boundaries. So let us consider 2-dimensional color code with boundaries. Then it turns out this color code with boundaries is equivalent to folded Toric code. So what is folded Toric code? Well, imagine that I have a Toric code with some 4 boundaries, smooth, smooth, and rough, rough. Then I'm going to fold this 2D Toric code into half. Yeah. So I'm going to fold this Toric code into half along this diagonal line, like origami. Then it turns out this folded Toric code is unitarily equivalent to the color code with boundaries. So I found this quite surprising. And so this may hint that maybe the key intuition to understand fault-tolerant implementability of logical gates is boundaries and folding ideas. And similar characterization is possible in higher dimensional color code. Finally, we proved that the transversal application of RD gates on D-dimensional color code is equivalent to generalized D-qubit control Z gate on D-decoupled copies of the Toric code. So what is generalized control Z gate? Well, that is just we use this D-1 qubit as a control qubit. We apply Pauli Z only when all these qubits are 1. But the point is, this generalized control Z gate belongs to PD, this level of the Clifford hierarchy. So it says that, so it turns out just a stack of Toric code saturate the Bravy Koenig bound. Okay, so if you are interested in this result, just come to me or Fernando or Alex. And the paper will appear, I think, online soon, in a week or so. Okay, so here to conclude, I would like to briefly talk about open questions. Well, just briefly, because there are many, many interesting open questions, and all of them are very important. For example, maybe we can talk about fault-tolerant implementability of logical gates in TQFT, and there is an initial work by Vivaland et al. And also, it may be interesting to think about the number of transversally implementable logical gates. This may be related, and this may lead to reducing the overhead of the magic state distillations. And finally, maybe we can think about non-local but finite depth unitary, such as lattice rotations or lattice translations, and so on. So again, there are many interesting open questions and many important open questions. So I think it's the right time for the community to start thinking about this interesting problem. So thank you very much for your attention.
Are there any questions?
So do all your results on normal subspace code apply to subsystem code that have local stabilizer generator?
Yes.
So in that case, it's straightforward. Okay.
I mean, yes, yep.
And the second question is, in your statement of the theorem for more general subsystem codes, you said if the code has a fault-tolerant threshold or something like that.
Yes.
What do you mean? I mean, and later you just mentioned like erasure threshold.
So I will state the theorem more in a precise way. So we assumed that the code has a finite loss error threshold, and the code distance grows at least logarithmically in the system size. Then the theorem holds.
Thank you.
Any more questions? Okay, I have a question. So you have this nice characterization of conditions which need to be satisfied to have non-Clifford fault-tolerant gates. But at the moment, we don't actually know very many codes which have fault-tolerant non-Clifford gates. I mean, we have the color codes and Reed-Muller codes and things like that. Do you think these results might show us where we might look for new codes, or maybe prove that the codes that we have are all there is?
So I think it's more related to our new paper on this project with like the color code and Toric code. And so yes, that is actually our hope, that by converting, so color code is, I think, the simplest example of such a code, and then we can convert it back to Toric code. So now maybe we can convert Toric code to color code, and maybe we can generalize such a framework to, let's say, we can use such a mapping to, let's say, has cubic code, which has large number of logical qubits. That's probably an interesting question to look up.
Any more questions? If not, let's thank Beni and all the speakers from this session. And before you go to coffee, Mick has an organizational announcement.